Let us start the second talk of this conference. The speaker is Professor Vijay Nadarajan. Professor Vijay Nadarajan is affiliated to the Department of Computer Science and Automation, Indian Institute of Science, Bangalore, India. He had his bachelor's degree in computer science and master's degree in mathematics from BITS Pilani and PhD from Duke University under the supervision of Herbert Resbrunner. He had visiting positions such as Zeus Institute Berlin and INRIA, France. He has elected as Fellow of Indian National Academy of Engineering in 2019. He had won the Swarna Jayanti Fellowship awarded by Department of Science and Technology, India, Government of India in 2016. He has got Young Engineer Award in 2011 and Microsoft Research India Young Faculty Award in 2011. His main area of interest is in topological dynamics, in broad sense, the scientific visualization and computational topology. He has published many papers in reputed journals and given many invited talks around the globe. As far as I understand, he has 7 PhD students and currently advising 4 students for PhD. I thank Professor Vijay Nadarajan for accepting my invitation to deliver the talk for this conference, and I invite him to deliver the talk on topological descriptors and scalar field comparison. Professor Vijay, please.
Thanks very much for the invitation, Vinod. I hope all of you are kind of having a good conference so far. I know this is a hybrid event, and I hope you are able to get the best out of both worlds, face-to-face interaction and also some of these talks. And I hope to engage with all of you during the course of this talk. Let me share the screen, and while doing that, I also want to mention that I'm happy to answer questions. If there are quick questions during the talk, please feel free to either write it or ask the question. In case I don't see the chat, I request one of the organizers to kind of ping me so that I can go and look at the question and answer. Let me go into full screen mode and then we'll begin. So thanks once again for having me here and giving you a quick overview of some of the recent results that have come out of our group. So the topic of this talk is broadly topological data analysis, so analysis and visualization of scientific data. The specific results that I'm going to talk about are centered around topological descriptors and how they help us understand data via a comparison-driven visualization. And that's what we're going to see today. But before I begin the talk, let me start with a quick introduction about where I come from. So I work at the Indian Institute of Science, one of the oldest universities in the country, located in Bangalore, a very scenic and beautiful campus that you're welcome to visit any time of the year, and it's still nice and beautiful. So within ISC, I'm a faculty in the Department of Computer Science and Automation, or CSA as it's called. CSA is a kind of a young and vibrant department with which attracts several bright minds to its PhD program and to the master's program. Several of our faculty is also fairly young, with several faculty members joining in the last 5 to 10 years, with a strong presence in multiple areas, including theoretical computer science, computer systems, primarily programming languages, and so on, and data analytics, machine learning, AI, and visual computing, something that I am personally interested in. within the department, we have a group that focuses on problems in visualization and graphics within the VGL or Visualization Graphics Lab. One of the primary focus of this lab is the study of topological structures and explore their application to the study of data that comes from different science and engineering disciplines. So we design algorithms for computing these topological structures, for comparing them, for storing them, for measuring them, and for making sense out of data using these structures. We design visualization systems based on these algorithms that help scientists from different disciplines to make sense out of the data. So on the left, you see data from computational fluid dynamics. Then left to right, the next you see data from these large-scale structure of the universe in cosmology, to the study of sand particles, granular materials, and to the right, data from biology, particularly the study of proteins and channels in transmembrane proteins. If you want to know more about what's ongoing work in the lab, I ask you to go and look at our webpage. Or if you're interested in looking at videos, then please take a look at our YouTube channel, VGL IISc. With that, let me jump into the topic of today. So I want to start by talking about data. So data comes in different shapes and forms. For the purpose of this talk, we are interested in data that comes from imaging devices. For example, data that is that comes from near-infrared microscopy that helps us understand tumors, for example, in the breast, or data from electron microscopy that helps us understand the structure of this human adenovirus. Data that comes from computed tomography, CT scans, that helps us understand the human anatomy and helps doctors or surgeons understand places where there are issues or fractures or any deformities that need to be fixed. Data that comes from simulations, for example, in the study of pore networks in material science, in order to design new and interesting materials. Data that again comes from simulations that helps cosmologists study the structure of the universe, or data that comes from other sensing devices. Broadly, these what is common among these data sets is that they are measured over a spatial domain, and they are represented as a scalar function, a real valued function over a spatial domain. Making sense out of this data is an interesting problem, and this is where visualization comes in. Visualization refers to the design of techniques for visual representation of data, beginning with classic visualization techniques such as isocontours, which help one understand, for example, here helps one understand the terrain by plotting curves which are constituted of points having a same function value. So each curve here represents a collection of points at a given altitude. Isocontours extend to 3D, where we have isosurfaces. Isosurfaces play an important role in the understanding of three-dimensional data. As you can see here, different surfaces of interest can be extracted as isosurfaces from a 3D volume. This helps us extract and understand the bone structure or the skin structure and so on. But this technique quickly becomes difficult in practice, specifically when the data becomes large and feature-rich and the isosurfaces become complex. Another technique that helps visualize data is volume rendering, where one presents the entire data using color and transparency. This helps understand the entire volume by presenting a picture of the data set. Again, this becomes difficult to understand and explore once the data becomes large and feature-rich. In presenting data visualization, I have essentially introduced to you some of the challenges that we face in the use of visualization techniques that were developed 10, 20 years ago. So some of the current challenges in visualization arise due to the increasing data sizes and the data becoming feature-rich with the availability of high-resolution data that comes from simulations that are run on supercomputers. It becomes difficult to visualize and understand this data. This is further accelerated because of the presence of data such as dynamic data that varies over time. The sizes are even more larger here. And ensemble data, which is a collection of data that come from repeated runs of a simulation using different parameters. All this is possible thanks to improved computational and resources and the availability of storage devices that helps us store and quickly access these data sets. So this increase in feature richness of the data necessitates new techniques for visualization. The classic techniques do not work anymore. One example of a new technique or a new paradigm for data visualization is the creation of visual abstraction. So abstract representations of the data. For example, using topology or topological analysis. This helps bring down the complexity of what you want to display on the screen and help understand the data. A related approach is via comparisons between different visual abstractions. Let me explain this using a very simple example that all of us should be able to appreciate. Let's go to the one of the examples that I showed earlier on computed tomography. On the left, what you see is a CT scan image, what is called a volume rendering from a CT scan, where we see through the entire volume. The data is mapped to color and transparency and helps us look at, for example, the bone structure with a little bit of context, the skin. A surgeon or an anatomist who is trying to understand this data will have specific regions that they want to focus on, or specific features that they want to focus on. They may not care about the entire data set. So the classic technique does not help us pay attention to these features of interest. This is possible once we have a visual abstraction, which is what is shown on the right. Essentially a tree. This is called the contour tree. I will introduce this later. This abstract representation of the volume helps the anatomist or the surgeon select regions of interest. For example, individual arcs in this tree are selected to highlight, for example, the lung or the colon or the bone structure. And the rest of the volume is represented just for context and with a lot of transparency. So this visualization that highlights the regions of interest is what we would like to achieve by using this visual abstraction called the contour tree. So hopefully I have given you a flavor of how a topological structure or a visual abstraction helps improve the visualization from something that you see here to something here, which highlights the regions of interest. Now, this visual abstraction, of course, helps generate these high-quality visualizations. But in addition, it supports quantitative visualization. It allows for measurement of these regions of interest. And these measurements can later be converted into statistics for further analysis down the stream. Okay, so why topology? Why use topology for visual abstraction? Some of you have a background in topology, I understand. I also know that one of the centers that's organizing this conference is one of the few unique centers that focuses on topology. Wish the very best for this center. So topology is the study of connectivity of space. So I'm essentially introducing topology for those who may not be aware of this. So this is a branch of mathematics where one is interested in how a particular space is connected, and we often use this this example from popular literature, where we say that a topologist is one who does not distinguish between a coffee cup and a donut. While this is easy to state, this is actually a deep statement. It essentially means that we care only about those properties that do not do not change when you deform a coffee cup into a donut. So topology comes with a rich history, and you can trace its history back to Euler and the problem of the 7 bridges of Königsberg. So what do we mean when we say we are interested in the study of connectivity of space? We are interested in studying invariants that help us identify when two spaces are equivalent, or help us distinguish between two spaces and say that these are not the same. So topology is essentially the study of such invariants. The invariants can be very simple, your Euler characteristic or number of connected components that you may have studied in graph theory, to more sophisticated invariants, such as the number of holes or tunnels in higher dimensions, and in one dimension higher, the number of voids that are enclosed. These are invariants that help us distinguish between different spaces. In order to be able to compute such invariants, we use ideas from algebraic topology. So these invariants are often captured in the form of groups, for example, homology groups. And that makes the whole set of invariants computable. So tractability is, of course, a next question that we would want to address. So the branch of study, so this is an interdisciplinary branch of study that uses topology for analyzing data, is called topological data analysis, or TDA for short. So what do we do in the area of TDA? So it's essentially the study of various geometric and topological tools towards the analysis of feature-rich or complex data. As a part of TDA, we design algorithms for constructing representations of the topology of a space, for algorithms for efficient storage of these structures, algorithms for measuring them and for querying from them. On top of this, these tools are used with techniques from visualization, from data analysis and statistical learning to help understand or make sense out of the data. TDA is a highly interdisciplinary field. It uses ideas from computer science, the design of fast, efficient algorithms, parallel algorithms, approximation algorithms, ideas from computer vision, graphics, and visualization, And of course, the core ideas from mathematics on algebraic topology and homology, Morse theory, and so on. And increasingly, the use of ideas from statistics and optimization, namely machine learning, manifold learning, and so on. Within the past 10, 15 years, since TDA has become a big field, there are lots of applications, very diverse, going all the way from sensor networks, material science, medicine, all the way to sports analytics. So with that introduction to the area and to the use of topology for data analysis, I want to talk about one or two topological descriptors. The two topological descriptors that I'm going to talk about are similar, so essentially one. Let me jump in and talk about the first descriptor, and then talk about how it helps us with data analysis. So we focus on the study of scientific data, like I mentioned earlier, and this data is represented as a scalar valued function. Let's call it f. So f here is a d-dimensional function and takes real values. So here is a graph of this function. So this is a specific instance when d equal to 2. So the graph is essentially a surface. And what we see here is a sweep over this surface in the direction of increasing values of f. So essentially, we are sweeping the surface bottom to top in terms of increasing values of f. In this case, f is the increases vertically upwards. F can be any scalar function. Just for simplicity and for use of for reasons of ease of illustration, we use the height function or the vertically increasing function. So let's look at this sweep again, and we will notice that the tree that is overlaid on top captures what is called the level set topology of the pre-image, right? So the boundary of this black region is called the level set or isocontour. It's the collection of points which have a given function value. If you track the topology of this level set or isocontour, what you get is the tree. Let's look at this one more time. And now that we have understood the definition, hopefully it will be clear. So as we sweep from down and go up, we hit the first minimum, and that corresponds to a node in the tree. And then a single arc, we hit the second minimum, and another arc joins in, and these two level sets merge to generate this third arc, and then a fourth arc continues. And the level set splits here, and hence the two different arcs that emanate from this one node. Right? And the level set terminates at this maximum, local maximum. So let's see another termination event here. When a level set splits at this node, which is a pass, and it goes up and terminates at this local maximum, after which it also terminates at this other local maximum. So you can already see that the topology of the level set changes at the local minima, shown in blue, where a new component of the level set is born. The level sets merge at these green saddles, or they split again at green saddles, and they terminate at the red maxima. So this tree is called the contour tree, and it represents the evolution of the topology of these level sets. It can formally also be defined as a quotient space given by the equivalence relation in terms of the level set. A few points to note here. The contour tree or arcs in the contour tree represent features in your surface. So the green-blue edges, green from the saddle to minimum, represent a valley. whereas the green to red edges, the saddle to maximum edges or arcs represent a mountain. So these are topological features, what we refer to them as topological features. And each such feature, a maximum or a mountain or a valley, is represented by the endpoints that determine the birth and death of this feature. So, for example, this maximum was born at the saddle and dies at the maximum. So hence, the topological feature, namely the mountain, is represented by a saddle max pair, the endpoints of the arc. The size of this feature of the mountain can be measured in different ways. We like to measure it using an analogy of lifetime. So during the sweep, we want to look at how long this particular feature was alive. So for example, the feature, this maximum, was born at the saddle and it dies at the maximum. So hence the topological feature size is the function value at the maximum minus the function value at the saddle. So this is called topological feature size. This is related to the notion of topological persistence, if you have seen this elsewhere, but it is there is a minor technical difference. So this is only for those who have seen the term topological persistence. For others, this does not. This is not relevant. Okay. So let's talk about the topological structure descriptor of interest to this talk, a merge tree. Similar to the contour tree, the merge tree also represents evolution of topology, but now of sub or super level sets. So a sub-level set is the pre-image of the interval -infinity to C, and the super level set is the pre-image of C to infinity. Unlike the contour tree, the merge tree has only merge events. There are no split events, hence the term. Depending on the sweep direction, we get either a split or a joint tree, but we uniformly call them as the merge tree. So what you see here are the two trees, the tree from the minima that gives you the merges on the sweep up, and the tree with maxima, which gives you the merges as you sweep down in function values. Again, here, there is the notion of a feature size, which is represented using the lifetime analogy. So a size of a mountain or a valley here is given by the endpoints of the arc that represents it. Arcs can be collected together. So in some cases, it will be the endpoints of a path between a maximum and a saddle, right? So this is what we call as topological feature size, and we are going to use these pairs later when we use the merge tree. Okay. So with that introduction to two topological descriptors, let us jump in and talk about how do we try and compare these merge trees. So our goal is to design a comparison or a distance measure between merge trees. We want this distance measure to satisfy several provable properties. In addition, we want it to be amenable to efficient computation and a easy and quick implementation, perhaps parallel scalable implementation. In addition, we would like the distance measure to be easy to interpret and hence support data analysis. So one of the solutions for such a measure is what I'm going to describe today. This is called MTED. It stands for tree edit distance between merge trees. TED stands for tree edit distance. Was there a question? Probably not. Okay. So the one of the fundamental ideas behind the design of this distance measure is an edit operation. So we want to, given two merge trees, we want to design a distance measure between the two trees by talking about how you can transform one tree into another. And the atomic operation that we want to employ to transform one tree into another is an edit operation. Let me introduce these edit operations first and then talk about the distance measure. So what is a tree edit operation? We talk about three different operations. So in the following discussion, I use the term lambda to denote an empty node or a null node. An insert edit will insert a node Q into a tree. Very simple. So we talk about this as lambda going to Q, or a null node going to Q, essentially inserting Q. Q can be inserted anywhere in the tree. It can be a saddle in this case, or it could also be a minimum or a maximum, in which case it will be a leaf node. Right. Similarly, we have a delete edit, where we remove an existing node. Right. Again, the node that you delete can be an internal or a leaf node. A third edit is called a relabel edit, which replaces P with another node Q. Now, this relabel essentially means that you change some of the attributes of P and hence get a new node Q. Right? An attribute could be the scalar value or the location. So we have three simple edit operations. We want to associate costs with these edit operations. Let's talk about the cost of these operations. The cost of an edit can be considered in terms of the topological features that are represented by the node that is being edited. If you think about it, all these edit operations are based on a node in the tree. So what is the cost associated with an insert? When you insert a node into a tree, this comes with some cost that depends on the weight of that node. Now, in the context of a merged tree, we know that every node has a pair, which this pair together represents the topological feature. So if you have a saddle, then it is paired with, let's say, a minimum, which is a leaf, and this pair represents a valley, right? And this topological feature size is what we want to use to determine the cost of inserting this Q, right? One way to look at this is in a diagram where the x-axis denotes the birth of the feature, the y-axis denotes the death. So insertion of Q is shown in this way. So this node here, this point here in the diagram refers to the node Q, and the coordinates are the birth time associated with Q and the death time associated with Q. So this essentially, this is what it essentially means. Q refers to one of the endpoints of a topological feature. So you can think of it as a valley. There is a birth time associated with the valley and a death time associated with the valley during the sweep. Those birth and death times are used to represent this point on the plane. A point on the diagonal is one which is born and dies at the same time. So essentially a null, right? That's lambda. So the cost associated with insertion, that is lambda going to Q, is the cost associated between these 2 points on the plane. And the way we describe it is as the length of this edge divided by 2. So this fraction of 2 is introduced for technical reasons. We want to associate this cost both to Q and to its other endpoint, and hence the factor 2. The cost of a delete works similarly. There is a deletion, and the deletion takes us from a point down to a point on the diagonal, right? And the cost is similar. Third, we have a cost of a relabel. So where you have a P going to Q, this cost can be incurred in 2 different ways, and we pick the smaller of the 2 costs. We could transform P into Q, and this can be captured as the maximum of these 2 lengths, right? So the maximum cost, so this is like your L1 norm, right? So that's the cost. Well, I'm sorry, not L1, the infinity norm, right? Another way to transform P into Q is to go from P to lambda and then introduce Q. So essentially go from lambda to Q, right? Or the other way around. So that's captured in this second expression. So the minimum of the 2 gives us the cost of a relabel operation, P to Q. Right. Okay. So with that discussion on the cost, yes.
Can I ask a question, Vijay?
Yeah, please.
When you consider an edit operation, do you admit that this operation can cause multiple events? I mean, for example, a multiple saddle joining many components. I mean, are you considering just the cases where you have one event, or cases where you can have multiple events?
Right. Yeah. Thanks, Patricio. Good to have you here. Yeah. So that's a very interesting question. Let me repeat that. So the question is, do I restrict myself to single node edits, or do I allow for multiple edits, right? Or so this is possible. So the answer to the question is yes. What I am introducing now is the atomic operation. But I do not want these atomic operations to exist in isolation. They do exist in isolation for a generic tree, but we are talking about merge trees. So if a saddle is inserted, we would like the corresponding pair minimum to also be inserted, right? So that's one of the restrictions we will bring in later when I talk about mapping. So that's partially, I think, answers your question. The other, I think, aspect to your question is what kinds of nodes can I insert? So I can insert all nodes, whether it is a saddle or the root or a leaf. And I can relabel any node to any other node.
I see. Thank you. Thank you.
Okay. Thanks for the question, though. So, so next I want to talk about this issue, which is mapping. What kind of mappings do we want to support, and what kind of mappings do we want to restrict ourselves to? Right? We want one-to-one mappings to begin with, right? We'll see how all other mappings can be built on using these restrictions. We want a node to be mapped to another single node when it's a relabel operation. We do not want many-to-one maps. We want maps to preserve ancestors. So if I2 maps to J2 and I1 maps to J1, further, if I1 is an ancestor of I2, then I want J1 to be an ancestor of J2. I do not want maps like this. And the reason is kind of intuitive, right? I would like a merge tree to be transformed into another merge tree. Such a mapping, while it makes sense for generic trees, it doesn't translate into a transformation of the scalar field that comes with this tree to the scalar field that is associated with this tree. So hence we want ancestor preserving mappings. Computing these mappings is known to be NP hard. So we do want to further restrict the kind of mappings. One of the constraints we incorporate, again motivated by the fact that we want this to be applied to merge trees, is that I want disjoint subtrees to map to disjoint subtrees. So here is a set of mappings that is legal. So I1, I2, I3 are disjoint, and they are mapped to disjoint subtrees. Whereas here, this mapping is does not map disjoint. These three are so J3 belongs to a different subtree, right? Whereas I1, I2, I3 belong to the same subtree. So this mapping is not legal in our constraint setting. So after incorporating this constraint, we get a polynomial time algorithm. So this constraint is both meaningful, and it also allows us to compute the mapping in polynomial time. To summarize, we focus on constrained edit mappings, this extends to unordered k-array trees, not just to binary trees, again in reference to the earlier question. And the extension is fairly straightforward. We would like the edit operations to correspond to persistence pairs. So hence, we don't want entire subtrees to be removed. We want nodes to be removed in pairs, or nodes to be inserted in pairs. Right? And the cost of the edit operations clearly depends on the scalar function. Right? So this is an instance of something that we do not want. I do not want this entire subtree to be removed, because the resulting tree is not a merge tree, because there is this hanging node. So we disallow such single edits. Okay. So this, putting all this together, we get MTED given two scalar functions and the corresponding merge trees. The MTED is essentially defined by transforming T1 into T2 using a collection of or a sequence of edit operations. So if E is the sequence of edit operations where the individual edits are E1, E2 through EK, and gamma of EI is the cost of each edit, then the cost of the entire sequence of edit is just the sum of the costs of the individual edit. The distance MTED between T1 and T2 is essentially given by the minimum of this gamma over all sequences of edit operations. And if your individual edits, so which is gamma of EI, are satisfy metric properties, then one can show that the resulting distance, the resulting measure is indeed it also satisfies metric properties. Right? Okay, so that is essentially the definition of MTED. Let's quickly talk about computation. I see that I don't know if there was a question. Okay, I think that's not a question, it's just feedback. Okay, let's. So again, given two scalar functions and assuming that the merge trees are also given, right? There is a nice dynamic programming algorithm due to Zhang several years old, that works for unordered labeled trees and supports the constraints that we talked about. And the algorithm is based on a recursive formulation. Of course, it has to be modified to work for merged trees, but that's a technicality that I will not go over here. The running time of this algorithm is polynomial. It actually depends on the size of the two trees and the degree of the nodes of the trees, which is fairly good. And in practice, the running time is much faster than what you see here, definitely subquadratic. Just to put things into perspective, there are different measures described available out there, right? And what I'm going to present is definitely not an exhaustive list. These are just some related measures. There are many measures described for merge trees and its and contour trees and their generalizations, read graphs. Several of these measures have been designed from a theoretical perspective. They come with very nice properties. They all are metrics. They all satisfy interesting properties called stability and so on. But often these measures are not tractable computationally. They take exponential time. There are similarly, there are several measures introduced from practical perspective. These are simple to define, efficient to implement, but often the structure of the tree is ignored in coming up with this measure, and hence they do not satisfy guarantees. TED is a good middle ground. It leverages the merge tree structure and is hence sensitive to the structure of the tree. There are some provable properties. The metric property is one. The runtime is good. It's polynomial. The implementation is based on a simple dynamic programming table, quick to implement, and it can be even implemented using existing libraries that support matching and so on. Further, TED or MTED supports finer grained analysis for comparisons. So what does that mean? Let's look at the two trees here. The tree on the top, let's call that T1, and the tree on the bottom, let's call that T2. These are two merged trees whose roots are here. I and J are the roots. The leaves are, in this case, maxima. We notice that globally the two trees are different, right? But if you look at a local analysis, this subtree is similar to this subtree, and likewise. And in fact, this entire subtree of T1 is similar to this subtree of T2. So there, two trees may be globally different, but they may share a lot of similarities. And in practice, we often want to capture such similarities at the finer grain or local structural similarity. So while existing measures support global comparisons, they do not support such finer grained analysis. Whereas MTED, we showed in later work, we showed that MTED does support local comparison via a subtree comparison approach. This we call as LMTED. Okay, so with that introduction to the distance measure, let's talk about how a comparison-driven analysis can be derived using these topological descriptors. Let's look at some simple examples to understand the power of MTED. So here are three scalar functions. On the top, they are shown using a color map that goes from blue to red, blue being low values and red being high values. So the maxima are at red, as you can see. These three functions are very similar to each other with minor differences. On the next row of images show the exact same function, where the maxima and the mountains associated with them are highlighted using distinct colors. Let's look at the correspondences between the two pairs, the left and middle, and then the middle and the right. Using the tree edit distance, we actually get the correspondences. So the color of the nodes here indicate the color of the mountain in these figures, right? So the brown, for example, corresponds to this mountain, and we see that is determined as corresponding to the brown in the middle scalar function. So what is shown here is the merge tree of the scalar function 1, and this is the merge tree of the scalar function 2. We see a nice correspondence as expected. Similarly, we see a correspondence here between the middle function and then the one on the right. If we try to identify correspondences using other methods, such as bottleneck distance or Wasserstein, which is well known in the literature, this quickly leads to problems. For example, when comparing the left and the middle, a simple Wasserstein, which is based on optimal transport, it does not find a correspondence between the browns. One of the reasons is that the scalar value range for this brown segment and the segment here do not overlap. And for this simple reason, we do not find this correspondence. There is an alternate correspondence between the brown and pink here. This is again due to the fact that there is an overlap in the scalar function range between the brown and pink, right? And hence you see an incorrect correspondence. So this can be fixed by considering the merge tree structure, and that's one of the reasons why TED is able to, or MTED is able to capture that similarity, because it imposes further the ancestor preserving property of the correspondence. An important application of this comparison is towards the extraction of symmetry in scalar fields. When we have a scalar field such as this, we would like to discover that M1 is similar to M2, both in terms of geometry, right, and in terms of the scalar value. So we want to find such repeating patterns, M1 and M2, where M1 is a geometric copy of M2 via some transformation. We want, in addition, that this transformation preserves the scalar values. So the problem here is to identify all such repeating copies, M sub i's, and this is computationally intractable because there are several such subsets, and it's not possible to iterate over all subsets in order to identify the repeating copies. So that's the challenge. One solution towards identifying symmetry is via visual abstraction, namely the use of topological structures, the contour tree or the merge tree. Symmetry is something we see in practice in living organisms, in virus, for example, in protein molecules. Often here, the symmetry is used to even solve for this structure from imaging data. Symmetry is seen even in engineering applications. In some cases, the absence of symmetry is an indication of something that's interesting. There's clearly a motivation for studying symmetry in scientific data. So here we have a cryo-electron image of a protein. In this case, it's called it's a protein kinase. It's an enzyme. We pre-process this data to identify some repeating units, that each of these repeating units is represented by a tree, and we run MTED over these collections of trees. So there are, in this case, I think there are 9 trees, and we run the MTED between all pairs of trees. We identify 3 pairs are similar to each other. So what you see here in this matrix is the values of MTED, with low values color-coded using blue and high values color-coded using red. So there are 3 pairs which are copies of each other, essentially, because the MTED values are very small. This corresponds to this symmetry here. And there is another pair of, another collection of 6 regions which are copies of each other. That refers to the symmetric copies here. Okay. So this is one of the applications of MTED towards identification of symmetric copies of a feature within a data set or between 2 data sets. A web server that helps extract and highlight symmetry is available from our lab, and this focuses on electron microscopy data. So if you are interested, I encourage you to go and take a look. The technique used to extract symmetry here is different from what I described in this talk. And nevertheless, the application is exactly what I described here. Now, let me wrap up with this application and say that one of the steps required for extracting symmetry earlier was identification of the regions of interest. Now, this was a manual step. With LMTED, we are able to remove this restriction and explore the set of all subtrees and generate such a distance matrix that helps us further analyze and understand what are symmetries at different length scales. So this matrix was computed for a given data set with no manual intervention whatsoever. Understanding this distance matrix and essentially extracting blue regions, blue submatrices out of them, helps us extract the repeating copies in this influenza A virus. So this essentially helps us capture symmetry at different length scales. So at the lower length scale and at the higher length scale, which is larger regions that are copies of each other. Okay, there are several other applications of MTED. I'm going to have to rush through them in the interest of time. So there is a study of flow behind a cylinder, and the extraction of MTED between the data set at different time steps helps us capture different stages of this simulation, beginning with an initial stage where there are no vortices to a next stage in the distance matrix, which corresponds to the formation of vertices, and a third stage where these vortices exhibit what is called shedding, so a periodic behavior, and a final stage when the vortices are distorted. We are able to identify periodicity in this vortex shedding data set by comparing each time step with every other time step and plotting such a distance matrix. The blue lines here indicate the periodicity, or essentially the time steps which correspond to the first time step. This is just the same distance measure plotted as a time series. We are also able to use MTED to compare shapes and essentially identify shapes that are similar to each other within a large database. This database has shapes which come from, for example, those of dogs in different poses, and gorilla in different poses, and the horse in different poses. We compute a so-called average geodesic distance, compute the merge tree on this distance, and compare all pairs of merge trees and plot this distance matrix. So what we get on the diagonal after reordering the rows is collections of data sets that belong to the same category. For example, the dog and gorilla and so on. There are some off-diagonal blue regions which are also naturally similar because they correspond to, for example, here it's two different human actually sculptures. One is David and one's Michael. So to summarize, I presented an approach towards data analysis and visualization that uses topology as a central representation of features. So this approach was combined together with an approach that is based on comparison to support feature-directed visualization. Specifically, I talked about a tree edit distance for merge trees. This tree edit distance is intuitive, has a good cost model that corresponds to merge trees. It can be computed efficiently and has several applications. I talked about only a few applications in this talk. We try to release all softwares. MTED is going to be released soon. If you are interested, watch out this space. And some of the videos describing the results and the technique behind MTED are also available on our YouTube channel. I encourage you to go and take a look there. I want to thank everyone from VGL for all the work done as a part of this project. Specifically, what I described today is the PhD work of Raghavendra. And of course, I want to thank all the funding agencies. And we are always looking for hiring postdocs and PhDs, master students. So if you are interested, feel free to look at our department's webpage and apply. There is also a startup Mimic that is based out of some earlier work that happened in our lab. And this is a startup co-founded by a PhD student of mine, Mimic. So if you're interested, they also have job openings. So I want to stop there and thank you for your attention. I'm happy to answer questions. Yes, there's one, and yeah, please.
Can I ask? Okay, first of all, thank you for your very interesting talk, Vijay. I would ask a question about symmetries, maybe from a different perspective, but about symmetries. Sometimes we know from the very beginning that there is some symmetry in the object we are considering. There is this kind of prior about the object.
Yeah, yeah.
In this case, did you consider the possibility of using symmetrical edit operations in your method? I mean, when you make some operation on one side, you could do the same on the other side, something like that. Did you consider this possibility?
Yeah, no, that's a fascinating thought. So this is something that I have considered. So symmetry in scalar fields is something that we have been working on for the past about 10 years now. What you mentioned was, I think, the starting point for our study on symmetry, right? So specifically in geometry, when we want to apply edits to a mesh, right? We would like these edits to be symmetrical, right? So if I want to change one nail on let's say on a character, or one finger on a character, I want that edit to be applied to all the fingers because the fingers are all symmetric copies of each other, right? So yes, so this is definitely possible. but we did not find a suitable application that that required us to impose this restriction, right? This is surely possible because, for example, we have the cost of the edits, we have the cost of all edit operations. We can easily cluster them together and impose this restriction and say that if I apply an edit on one of the arcs, then I apply the same edit on all of them. So they come as a group, right? I could impose that. If there is a nice motivating application, I'm happy to look at it. But yeah, but that's interesting. It was one of the first questions that we asked before we talked about symmetry in scalar fields. This was even before the discussion on MTED and all that. We have a couple of papers on what it means to talk about symmetry in a scalar field and how is it useful. This is from 2011. Yeah.
Thank you, Vijay.
Sure. I think there's another question from
Sir.
Yes.
Sir, suppose if we have some sampling, some data set, how can we decide that certain point is the saddle point or certain point is a critical point? How can we decide it?
Okay, yeah, that's a valid question. I could not go into that today. We all understand that these critical points, if the function is an analytic representation of the function is available, then you can talk about gradients, right? But we are talking about functions that are sampled and represented using linear interpolation, for example, or some higher order interpolants. So in this case, identification and classification of the critical points can be done via a combinatorial procedure that looks at the neighbor vertices and computes what's called the link of this point under consideration, which is a vertex, and compute the link, which is your one neighborhood, right? And the classification of critical points is based on a classification of the topology of this link and the function values of vertices in that link. So let me give you a simple example. In 2D, every vertex, if you look at its neighbors, right, the link is essentially the one sphere, so the circle neighborhood, right? So the neighborhood of every vertex is a collection of vertices that together form a circle in simple geometry, right? Now I can look at all these points and look at which ones are higher, which ones are lower than my current vertex. If all of them are higher than the vertex, then I know I am a local minimum. If all are lower, then I know I am a local maximum, right? So a saddle is one where the number of components of lower vertices, right, is greater than 1. So you can think about this a little bit, and then it will be obvious, right? But there is a formal proof that this indeed works. There is a work by Banchoff, which proves that this combinatorial procedure does indeed help classify critical points, right? So this is called the lower link based classification, if you want to look it up.
Thank you, sir.
Queries? It was a very informative session with a good explanation of topological descriptors, comparison between descriptors, tree edit operations, etc. Also, the visualization and graphical interpretation gave a clear picture of the context. Thank you so much, sir. So our next talk is at 12:30 p.m. by Patricia Frosini on approaching topological data analysis and geometric deep learning through group equivariant non-expansive operators. So we'll start at 12:30 itself. Thank you.
Thank you.
Thank you, Vijay.
Thank you. Thank